All right, without any further ado, you don't want to hear me talk anymore. I'd like to introduce Paul, who will be talking on the UEFI threat, or how I can permanently brick your computer. So please give a warm ShmooCon welcome to Paul.
Hey, thanks for coming to my talk, and thanks for ShmooCon for having me here. It's awesome. I want to start off with a question. When all of you nerds are all of you not nerds, I don't know if Jason from marketing is here, but when anyone buys a computer or is thinking about buying a computer, you have some requirements in your head. What are some of those requirements? Shout them out. Tyler, did you say like Pornhub in 4K? I mean, I'm not judging. I mean, the 4K part, okay. But we all have unique requirements, right, when we go out and buy a laptop, whether that's RAM, CPU, a nice screen to project in 4K, whatever that might be. There might be some security measures. How many people here consider the security of their firmware in UEFI? My goal of this talk is that by the end, everyone raises their hand to that question. So if I accomplish my goal and we get to the end of this story, you're going to be like, wow, the next computer I buy for me, for work, for my family, is going to have a better security framework and structure for UEFI. Your computer comes with software pre-installed. When you purchase a computer, most of us nerds, the software on there looks very different from the day we got it. I run Manjaro Linux because it's in my unspoken contract that I have to tell you I run Linux on my desktop. But we customize our software. We customize maybe our bootloader. We don't really, most of us, don't customize the firmware. It comes pre-installed from the OEM with all of this software or firmware installed on your system. That largely you don't have a choice about what firmware comes on your system. It's there to enable your hardware so it actually functions. The other thing is that it's not easy to modify or update. We'll talk a lot about exactly why that is. It has the highest levels of privilege on your system. We'll talk a little bit about privilege levels as well. Most users don't even know it's there, let alone customize it. In fact, I think you shouldn't really know that it's there. So again, this is the most highest privilege level. Like on the far right or left, depending on your perspective, we've got like Linux memes, right? And we traverse all the way down the stack. We go from the kernel to your bootloader, and then we get into this magical space called firmware. And this firmware has the highest levels, right? I'll spare you the ring diagram that I put in every presentation, but this is before the operating system, it's before the bootloader. Even your UEFI firmware within that, Intel ME and CSME have even higher privileges that we've labeled ring -3 on your system. With Intel ME, if your computer is off and is receiving power, that firmware is running and you're able to interact with it. And it has full access to all of the hardware and can trick the bootloader operating system into doing all kinds of things. So what is firmware? Firmware for me is just software that's inconvenient to program. We're really blurring the lines between what is software, what is firmware, and like most other software, firmware has a lot of vulnerabilities. And I'll definitely show you some of the research that we've done in order to prove to you that there's a lot of vulnerabilities out there in firmware, and specifically UEFI firmware. Now most people, you would want to think update your firmware, and you know, I'm not saying it was aliens, but you should update your firmware, and I repeat this all the time, but you probably won't. And after I analyze some of the data from our research team, that you're not updating your firmware. Like I'm looking at all of you and the people that you know that run, like you're not updating your firmware. Attackers are going after firmware. This is one of the things. I work full-time for a company called Eclipsium. One of the many research projects that I worked on was to look at all endpoint malware that was attacking UEFI. It was very selective. You can go to the link and read the full article. I know the text is really small. Nabromi is the only BIOS-based attack on there that I thought was cool enough to make the list. And in the blog post, I linked to all the information about all these different strains of malware. One of the ones that was most recent, Cosmic Strand, that is probably the best example that I can think of as to how the malware is able to traverse to those lower levels and trick the operating system. They did a great job of explaining how that malware works. I was really exciting. I'm like, but that really sucks for defenders. The last one, Black Lotus, we're kind of on the fence whether that actually existed. There was a UEFI bootkit for sale, supposedly for sale, on some dark market somewhere. I haven't seen any good evidence. I didn't include a reference to it as it did get some press. So there is malware out there looking to infect computers via the UEFI threat, which replaces BIOS on all modern PCs, laptops, and servers. I shouldn't say all, on ones that choose to implement UEFI. Now, a lot of you won't believe me. And you're like, this is an OEM problem, Paul. I actually get this response from people like, I should get my PC server laptop and the OEM should take care of all the security. If that were true, like, we wouldn't all need to be here working in security. We could all effectively go home, because whatever suppliers are giving us for hardware and software, if it was already secure, they wouldn't need people like us. And the fact is, the manufacturer doesn't always provide the highest level of security, and also things change where we uncover vulnerabilities or misconfigurations that make something vulnerable. And also, which manufacturer, an OEM or supplier are you talking about? Inside all of your PC servers, laptops today are multiple, probably over a dozen different pieces of hardware and firmware inside of your systems that have to be updated. And all of those have their unique supply chain that gets messed up as well. And in this talk, we'll focus specifically on your UEFI and specifically what's being stored on your SPI flash chip that stores some of the firmware, I should say, for the hardware inside of your computer and is instrumental in executing the process that goes from when you push the power on button to when you're presented with the login screen. That firmware is stored on an internal SPI flash. Now, many of you are probably far more advanced than I am in microcontrollers and using SPI to program such controllers. When I started studying heavily the SPI flash, it was in the context of your PC. And on your PC, and again, it depends. I work with a fantastic researcher, Jesse Michael, and I say I'm going to get him a t-shirt that says "It depends." Because every time I ask Jesse a question, I'm like, so but if you did this and the SPI flash was laid out like this, he's like, it depends. So just keep in mind when I present to you this information that there are lots of different chipset configurations, hardware configurations, data sets for chipsets that is going to change slightly what I'm going to present based on your chipset. You have to go read the data set for your chipset. So this is a rough example of what your SPI flash might look like on your computer. It's broken out into regions, and each of those regions store a different type of information. So your first region on your SPI flash contains your flash descriptor. Think of this, now, again, I only had 50 minutes for this talk, and a lot of this stuff is days of training that you should absolutely take from Zeno Kova. I don't know if Zeno's here, but that's how I learned enough about this stuff to actually have conversations with my researchers, which was awesome. So thank you, Zeno. If you want more, he's got 2 courses that talk about what I'm talking about in this presentation that I had to go through myself to understand it. So your flash descriptor, there could be another slide with the region layout, sub-regions within the flash descriptor. But think of your flash descriptor in this context as a map, a file system map, if you will, of the rest of the regions on your SPI flash. The other thing the flash descriptor contains is some access controls. Now there's lots of different access controls that govern what's stored on your SPI flash. We'll cover many of them in this presentation. So that's where it starts. Then you've got your BIOS region. That's actually where your BIOS or UEFI is stored. You've got Intel CSME or Intel ME, which has been put on all of your Intel-based computers since 2006. Maybe unbeknownst to you, there is a separate microkernel, microprocessor it uses the storage on the SPI flash and some dedicated memory and shared memory that runs within your system. The firmware for Intel ME or CSME is stored on your SPI flash. You've got Intel Gigabit Ethernet. This is basically configuration information, the best I can tell, about your Gigabit Ethernet adapters. The EC region is your embedded controller. So on your laptop, typically, you'll have keys that you can adjust the brightness on your screen and other such functions. That hardware is all controlled with firmware that's stored in your EC region. Platform data is like other data that OEM may have wanted to store on the SPI flash. So I don't have good research yet on what is actually stored there and what we could possibly do with it, but we are finding this on more modern computers that are being produced. So that is Intel, and so we're talking about Intel. Now, I'm not saying AMD and other processor architectures don't have a SPI flash or similar things. They do have similar things, it's just different. What I'll focus on here is Intel, because it's the most common, and I work with a bunch of people who used to work for Intel. So this comes from Zeno's older training, that original training that Zeno was talking about yesterday, and I had to study how the SPI flash was accessed in your computer. So it's basically two primary methods. You can directly interface with the SPI controller that's on your chipset, or more likely you're interfacing with MMIO. So it's memory mapped regions inside of protected memory, in this case, that you access, that brokers the access into the SPI controller that's on your ICH or PCH, which if you're building a gaming computer, right, they talk about what chipset are you running. The chipset is your integrated controller hub or platform controller hub. It's basically the central hub that has all the connections to the different pieces of hardware on your system. One of those pieces of hardware is your SPI flash. And access to that is a whole talk in and of itself, but basically UEFI creates a protected region in memory that sets up registers and access controls so that applications and programs and stuff can access things on the SPI flash to either read or write to your SPI flash. When you need to do things such as update your UEFI BIOS, swap out your secure boot keys, that all goes through this process. Again, there's like entire multi-hour modules in Zeno's training that explain all this work, and it's chipset dependent, so there's a lot of it depends in there. So if you're looking at this going, I think it works slightly differently, it probably does because it's chipset dependent. Okay, so one of the goals is we have to protect what's on the SPI flash, because if we're able to modify it, as you'll see, there's a whole section I'm going to talk about, air quotes, bad things could happen. So all of the settings, again, depending on the chipset, there are protections such as only when the processor is in SMM mode, system management mode, is a processor mode that locks operating system operations so that it can do privileged operations. What is required to be in SMM mode to be done is also like a register setting, basically, that says you can't update your BIOS or this region of the SPI flash, your BIOS region, unless the processor's in SMM mode. Also, I mentioned the flash descriptor, lays out access controls. Now, the thing that got me was when I started looking at systems, and I'll show you some results of some basic scanning tools that are open source, one of them being ChipSec, I was finding these misconfigurations from the OEM that didn't configure these protections that allows you to write to the SPI flash, and I was like, I kind of understand it well enough now where like, can I just fix it? Can I just change this stuff? It turns out you really can't. Like, it's tied to the hardware, and the registers have to be programmed in the UEFI BIOS. So in other words, I was talking with the researchers, I'm like, well, what if I change that? They're like, well, you could change it so the register behaves in a certain way, but the firmware that's installed on there doesn't honor that register, so it's not going to implement that security control, or there's just not a physical trace on the board that maps to that register, so you can change it all day long, and it's not going to take effect. That's why we have to go up the supply chain to the OEM to get fixes to a lot of the problems that I'll talk about. Okay, so there's 4 main protections. There's lots of other ones. Zeno's training goes into a lot more detail and like maps out those trees of all the different protections. I like to focus on the 4 protections that you can pretty easily find with open source tools like ChipSec. The flash descriptor, global write protections, BIOS range protections, and flash configuration lockdown. So one of the first things you can do, and I think it's pivotal to the story here, is you need to dump your SPI flash on your PC, right? You may have done this with other different hardware and microcontrollers. If we get a good dump, a clean dump of the SPI flash, we can do a lot of analysis with a lot of different open source tools. So this is your first step into looking at what's on your SPI flash. ChipSec is a great program. It came out of Intel. The founders at my day job were the original developers for ChipSec. And one of the nice things about ChipSec is on Linux, it loads a kernel module that accesses the SPI flash and creates you a dump file. Awesome. The next thing you can do is analyze that SPI dump and look at the configuration for your flash descriptor. I hope you can look at this and start to figure out what's wrong here. What's wrong with the permissions on the flash descriptor region on my SPI flash? We know RW is read-write. So hold on. This vulnerability persists, and we'll show some data next that shows how much it persists. If I can write to the flash descriptor region, I can change the rules. It's like leaving your firewall exposed to the internet with your management interface with no password and letting the internet write your rules. I can change the rules if I can write to the flash descriptor. Also, if I can overwrite the flash descriptor, here's our first example of creating an air quotes permanent brick. So if the protections aren't set correctly, this is bad, like I found on these systems that really aren't that old. The next ones are BIOS region write protection. So there's multiple levels. The backstory here, because it would take 30 plus minutes to explain each one in excruciating detail, but the takeaway, TLDR, is there are protections that force the system to be in SMM mode in order to write to your BIOS region. Intel realized there were some issues with that, so they added another layer of protection. So now as an OEM, I have to figure out which combinations of protections, whether I'm going to use the BIOS write enabled coupled with the BIOS lock, right? So I got to set BIOS lock. In order to undo BIOS lock, I have to set a register. Then they also added SMM BIOS write protection, so I can't just lock and unlock it. I have to make sure the system's in SMM mode. There was one of my favorite research papers of all time called Speed Racer. One of the authors was Corey Kallenberg, and it's just an awesome paper that you can read about that, and I have references to it, so don't stress if you can't find it. So that's BIOS write protections. But now there's attacks against it, but some OEMs just don't set these protection bits at all, which means I can write to the BIOS region. The other level of protection, number 3, is BIOS range write protection. So this is basically they're called, if you see the docs, FLAs, flash linear addresses, right? Really fancy language for basically the addresses where all the locations are in your SPI flash. You can apply protections to select ranges. So like independent of all these other protections, you can say, I want this range to be protected and no one should ever write to it, ever. And it's an additional mechanism to protect. However, like in this case, they didn't set those either. Once you've set all of this stuff, configuration and all the registers, you can then lock down your configuration. This one's interesting. The configuration is most often locked. I struggled to find a system that hasn't set, there's one bit there where line 15, where there's 15 in square braces, lockdown, flash lockdown, they lock the configuration. But all the examples I showed you came from the same system, and they were insecure. So they basically locked an insecure configuration for the SPI flash. Okay, so that was a primer so that I could now get into some research. When I started at Eclipsium, I saw this one line item on a spreadsheet that was tracking stuff that we wanted to publicize, and I was like, what's that? And it was this 5-year-old amazing research paper where we had analyzed all of these spy flash configurations in firmware, in spy dumps, and created this great document. And I went to one of the founders and I was like, Alex, what is this? And I'm like, did you ever release this? He's like, no. I'm like, can we? And that's why I'm here. That's actually what started this whole thing of me presenting here. I was like, dude, this is really cool. We have to talk about this. It's awesome. And then he goes, yeah, we should update the research. I'm like, that's even more awesome. So let's take a look at what we got. In our database, the other thing I realized at Eclipsium is that we crawl the internet and we download as much firmware, mostly UEFI firmware, that we can find on the internet, and we stuff it in a database, and then we had a data scientist who is an amazing, awesome ninja, Adriana, look at the data, and I was like, well, this is really cool. We've got all these firmwares, over 100,000 firmware. What's just some basic data that we can pull, right? We're still working on this. We're going to release some research papers as well, but we started looking at the data, and I was like, well, that's interesting. So across 138,000 firmware packages, we identified 198,000 CVEs just by doing a basic match in basic stuff. Again, this talk isn't about how we collect it or analyze it. I'm encouraging my researchers to give that talk. This talk is about the results and their implications and how we can fix it, which is kind of depressing because the number one CWE that we found is essentially the buffer overflow. And this is from a large data set. This is stuff that we know. If we were standing around drinking at the bar and I said, D, firmware's vulnerable. Dean was like, yeah. But now I have data to go like, no, firmware is really vulnerable on a massive scale. We haven't fixed the buffer overflow problem in a huge amount of software that's pre-installed on all of your systems, that's difficult to update, that has the highest level of privilege on your system. So I was excited about this, and now after I just said that, I'm a little depressed. I have something for that, though.
Bring it up for the whole class?
I did not. It was a gift. So the 2017 research. So I started with the largest data set. Now I'm going to start traversing down. The smaller the data sets get, like more information can be extracted. So the team analyzed 32,000 pieces of firmware and found that 3,400 corresponded to basically 502 modules lacking basic firmware protections. In the context of this research, we were able to pull the firmware image file, not the spy flash dump, but the firmware image file, unpack that, reverse engineer it, look at the spy flash and the descriptor region, and determine that it was missing protections. So that's what this data is referring to. MSI and Gigabyte account for a majority of those. But that doesn't mean if you buy server level gear that you're safe either, as you'll see in a couple slides. But, and I don't want to pick on people or name names, MSI, but when I got to Eclipsium, I was like, my friend Tyler said I should buy this awesome MSI laptop. And I'm like, this thing's great. 4K screen for looking at spreadsheets. And, but I looked at the UEFI, and my coworker's like, no, we don't buy MSI, because it is of the firmware. I'm like, you actually take that into account when you buy a PC? And they're like, yeah. And then I looked at it, my firmware is vulnerable, and it hasn't released an update in over 2 years. I mean, this was a laptop I bought 2020. There's no firmware update for it. It's misconfigured, it has vulnerabilities, and there's nothing I can do about it because the OEM has to put all those pieces together in the exact configuration. So, and we show that in our data. Some manufacturers pay more attention to this than others, but it's model specific. It's not to say they don't make mistakes, which they do. And again, trivial to install firmware implants or brick your system. Because the other thing is, if I'm starting to overwrite these regions, which I'll walk you through in a moment, that if you start mucking with that, you can't just apply an update. Updates are like a small update package, typically in a capsule, hopefully signed, which is something else we'll talk about in some other research, but that's just like a portion of the update. It's not the whole spy flash. If I corrupt the spy flash, I have to rebuild the spy flash, and your OEM has to provide that to you, or you have to take a backup of it, or you have to hope it has a backup spy flash which do exist on some systems. So this is kind of the breakdown. Intel, like their own configuration, they've locked this stuff down. They author chipsec, they know about this stuff. However, Intel has to hand their chips, the data set, the toolkits over to an OEM that's integrating this into their system and can make all of those configuration changes, which is why when it gets in the hands of Gigabyte and MSI, they make mistakes because they want to get stuff out the door, and they're trying to integrate it with all their hardware and software from other manufacturers. So that's kind of the breakdown of the 2017 data. Our updated data. So we analyzed over 15,000 live images. So these are not firmware images we pulled off the web. These are actual live systems that we were able to do a spy dump and analyze and see what was there for vulnerabilities. In almost every single one, we found a firmware vulnerability. Not because the fixes for that said vulnerability don't exist, largely because folks aren't updating their firmware, which is interesting. And these are live systems that come from a data set of like systems actually out in the wild. So again, people aren't applying their firmware updates because pretty much all 15,000 had some kind of issue. What kind of issues did they have? I analyzed a subset of that data as it was coming in, which is still, this chart is representative of the larger data set, as you'll see. And some of the issues, so 20% in my smaller data set had some kind of spy-related issue. Still a pretty good number of systems, and as you'll see in better cases next. The other thing was outdated DBX is the #1 vulnerability we're finding. That means people aren't updating the revocation list for secure boot on your systems. Folks, this is super important. You should definitely do this because it means there's vulnerable software that I as an attacker can take over and circumvent your secure boot process. If you're not updating your DBX, your revocation list's not getting updated. The other thing that was interesting was microcode. Spectre Meltdown, in a host of other microcode vulnerabilities, come down through your UEFI firmware updates that Intel like has to really, or AMD, whoever it is, has to go, hey, here's a microcode update. Then they have to integrate that into a firmware update. You have to apply the firmware update, which in turn applies the microcode update. And there's a series of keys that protect that validate that microcode update. And what we found was 45% of systems were missing some type of microcode update, which means you're not updating microcode. Okay, let's look at a little bit of the Dell and manufacturer-specific information. So out of our 15,000, we had 6,643 Dell-based systems. Now, what I find interesting with this data set is 1,846 of them are missing a BMC update. That's your baseboard management controller. Again, it is similar, very similar to Intel ME. In servers, right, it's a different manufacturer that may have basically an embedded system on your server that allows for management. And this can be really bad. As you'll see at the end, I will culminate with just how bad this could be. If there exists out there BMCs with default passwords, it means attackers can do really bad things with them without even really having to try. I mean, this is the same default password thing we've had on IoT devices since basically someone created the first IoT device. But what I also found interesting was there was a very similar number, even on Dell systems, that are missing protections on the SPY descriptor. So SpyDesk that's the chipsec module name. I apologize, I didn't put more English names in there, but that's the like -m common dot spy underscore desk looks at your SPY descriptor and specifically speaks to like missing protections on the flash descriptor region inside of that. So there was 1,700 of them. I mean, that's almost as much as the BMC. Like, what? That's a lot more than I thought it would be, because a lot of these, while these problems are known, they're not getting fixed out there in the wild, which is what the data was proving to me, which is something, again, I kind of had a feeling about, but here we are. Same thing with Lenovo, outdated DBX. Again, not updating your secure boot keys. Same, HP's better. So some vendors are better than others, right? So HP in this data, they didn't have as many unique devices in this particular data set, so that's why that data shows that. But certain vendors tend to be better than others, depending on the model, depending on the year, and also these vulnerabilities will not exist if you apply the patch. So again, super micro, more outdated microcontroller vulnerabilities, right? People aren't applying those as well. So I said, well, that data is great, but like I'm a nerd, I want to check some of my stuff and see where my stuff is falling in this spectrum of what's vulnerable and what's not. Because here I am working for Eclipsium, I'm like, I think I do a pretty good job of locking down my systems, but then I started running these tools on my own stuff, and I'm like, wow, I really kind of suck at security. Like I had this, I was really depressed. I have medicine for that. And I looked at my own systems, and I was like, all right, here's a system that has a relatively recent BIOS. 2018 was actually the latest release from that. And I believe this is this little Chinese Kotom device where the case is the heat sink kind of thing. And I was like, I got a great price on them. They run rock solid. They're awesome. I use them for my firewalls. And then I'm like, I lock them down, I install the latest version of pfSense or whatever, it's great. And then I said, what happens if I look at how the spy flash and everything is configured? And it's horrible. There's no protections on the spy flash, which means if someone can attack it, they could basically melt my firewalls and destroy them, which is terrible. So this system did not, and I don't believe this one even had a BIOS update. If it does have a BIOS update, I've yet to verify if it actually fixes the issue. That's the thing, is I don't see in the release notes, hey, there's an update, and by the way, we fixed all that heinous stuff that Paul keeps talking about to protect the spy flash. They don't say that. It's a crapshoot. So again, this was purchased in July of 2020, July of 2021, and the BIOS versions on each are the same. And so in this case, there was no update for the OEM. In other cases, there were. In this case, no update from the OEM. So these are pretty modern systems. I mean, think about if you buy a small firewall-ish type appliance to run pfSense, you get these little appliances, but they've got some pretty heinous vulnerabilities. This comes from a larger system. This is like an i9 system that I have in production today. Now, what's interesting about this system is that it's newer, so the BIOS release date is 2021. It has some updates. Again, I don't know if these updates fix some of these issues. I do know I get a microcode update, and so now, I do as I say, not as I do. I haven't applied this update because it's in production, but it has a microcode update. And I'm like, okay, that's cool. It doesn't say if it fixes the issue. The issue with this particular system is the manufacturer has left the UEFI configuration in manufacturing mode. Does anyone know the implications of what leaving a device in manufacturing mode has? Sort of like debug mode. If debug mode gave you the ability to fuse encryption keys on the board, which is a debug mode kind of function, that's what it does. So Intel has to deliver this hardware, software, and toolkits in manufacturing mode so that me as HP can go, I want to put my own keys on there, and then I want to fuse them to the board. It's not like the direct supply chain that Apple has where they control all the hardware and software. So like they don't have to, they do have manufacturing mode, but they control the whole process. Intel ships stuff with manufacturing mode open and leaves it up to dozens of vendors to go, I got to make my changes. Then I have to turn off manufacturing mode so that no one else can fuse the keys. If you can fuse the keys, you can not only break the system, but you can own the system in a lot of different ways. You can lock people out of running firmware other than attacker-controlled firmware. That's what some of these keys control. So in this case, the manufacturer that was probably MSI. Did I say that out loud? MSI, yeah. MSI shipped this and didn't enable manufacturing mode. It's a really, really, really bad bug inside of your UEFI. One, that Apple has made the mistake previously. If you read my article when I talk about this that I linked to in this presentation, Intel-based Macs for some certain period of time didn't have manufacturing mode set correctly, which is kind of interesting. So this is a mistake that OEMs can certainly make. And there's a lot of bad combinations. So chipsec will try and tell you about these different, they will say, you haven't set the BIOS control mechanism registers to enforce SMM mode if you want to write to your BIOS region. And they recommend you should probably put some protected range registers in there to protect that region. Then you scan for protected range registers, and the next circle is you haven't applied any protected range registers. So you've missed all of these protections like you're not even trying. Okay, so now we've underscored the importance of UEFI and all of these settings. We've seen that in the wild, a lot of these protections are still missing to this day, even though some believe this is a problem that has largely been solved. I think my data proves that it has not. So me, with my evil hat on, I'm like, so what happens if we try and do bad things? And I want to put a disclaimer over this part. Like, please don't use this information to destroy people's systems. The purpose of this talk is to show you that it's possible. I'm not going to give you a Python script that can go wipe out systems, because the only purpose of that Python script would be to destroy systems, and I don't want to see that happen. I want to show you enough that we believe that this is possible, and we should work to encourage both OEMs and everyone in the supply chain to improve this issue. But if we were going to be evil, you would overwrite the flash descriptor, again, which contains the map, again, which is writable, and not even just wiping it out, but corrupting it in some way could have ill effects on the system. So you could kind of start with the flash descriptor. It's kind of that base level. You have to protect the map, the base permissions that are on your flash descriptor. As we've seen, some people don't. If you start going in to overwrite that. Now, there's a lot of what ifs, and it depends to get here. We'll talk about some of those. But if you can write stuff to the flash descriptor, corrupt it in some way, your system is not going to boot. And it could be, the reason for the air quotes is permanently means I gotta have some way to rebuild it, right? I gotta have a backup of it. I gotta have another spy descriptor that has a backup of it. Or I have to go to my OEM manufacturer and get a clean copy of it. Let's now look at the BIOS region, moving up in the stack a little bit. So this has rules, a lot of different rules that we've talked about to prevent overrunning, right? Force SMM mode before anything can write to the BIOS region. Most more modern systems like my framework have done a fantastic job of not only setting BIOS region protections, but also protected range registers to protect this area. So, but if you were to start messing with stuff in there, you could lead to a bootkit or permanently bricking your computer. The other interesting thing is a sub-region of your BIOS region is called NVRAM. NVRAM is where UEFI variables are stored. My estimation on looking at UEFI variables is it's like the easy way. It's like not even fair. Like the amount of abuse that we have for NVRAM variables, for buffer overflows, for abusing protections or missing protections on them is really high. If you want to go find vulnerabilities in UEFI, I'll give you like a very simple tip. Go look for the function called getVariable. That's getting unstructured data and processing it. A large percentage of buffer overflows that we've seen that affect UEFI are in getVariable. NVRAM is where they're stored. Now, these variables have different protections. So not only do you have protections of the BIOS region of the SPY flash, but protection of variables. Those can be runtime variables. Those can be authenticated variables. It's like an entirely different set of protections. And you can kind of see where it gets confusing for OEMs to make sure all of these things are done, to lock all of these things down. There's a lot of steps. You can have spoken to people who may or may not have done this before. You can truly mess up a system or brick it through NVRAM variables. It doesn't require at full access. So, well, 10 minutes, okay. Intel ME, not only for management, if you mess with this, so this is not just like remote management. If you mess with this, it is integral to the system. There were previous cases where if you mucked with this and screwed it up, your system would not boot. It would boot, but it would turn off after 10 minutes. Because anti-theft used to be built into this, and you didn't configure anti-theft correctly, so you, permanently brick, like your system's got 10 minutes, then it turns off. And there's nothing you can do about that. Gigabit Ethernet region, really interesting in that if I corrupt this region, this is where your configuration's stored. Typically writable, because what do you do with your Ethernet adapters? Especially a lot of us. You change your MAC address. Well, it turns out that gets stored here, so it has to be writable. But if I wipe it out or I corrupt it, now I have to rebuild it. If I don't have the stuff from the OEM to rebuild it, I don't have an Ethernet adapter. I'm curious how much AMT or active management technology relies on that and doesn't function, which means even if your server's in a data center and you have AMT, it can't use the Ethernet adapter because I just wiped out your partition. There have been some research. In fact, yesterday I saw another one that was given at Recon on your EC firmware. EC firmware is interesting. I've seen Mickey and Jesse on my team have talked about hiding data there, but if you muck with the EC region, bad things could happen. Platform data is one where we kind of don't know. I don't know what will happen yet. This is more research that I want to do. I don't see a lot of research. If anyone wants to work with me on that or do independent research, let me know. I want to do some kind of heuristics across all of our 15,000 firmware images as a next pass to go, what's in platform data? What can we analyze? What can we do like a histogram plot to see what differs between it? Okay, so if you want to do bad things, you want to mess up systems, look at ChipSec. Academically, with permission, disclaimer, don't say Paul told me to go wipe out systems at ShmooCon and it was fun. ChipSec has the ability to do it. Flash ROM has the ability to do it. Little known fact, Flash ROM has the ability to do it as a non-root user depending on the configuration, which is kind of interesting. You can ask me about that after. RW Everything is a Windows application that attackers have used to do it as well. Also, be careful if you're working with your SPY flash, or, if you want to blow it up, don't be careful. Your EC controller uses the SPY controller to perform certain functions. If you're reading and writing from your SPY flash and interfacing with the SPY controller, your EC controller can interrupt that. It's kind of interesting. It could cause a bad read or a bad write of your SPY flash. A bad write would cause a brick. So there's kind of my tips for if you want to blow, well, not really blow stuff up. We'll get to that. Hold on. So why can't we just lock everything down? Because there's too many cooks in the kitchen. Intel releases a chip. Gigabyte makes a motherboard. The UEFI vendors, Inside, American Megatrends, Phoenix have a play, Dell, Lenovo, HP. All of these vendors have to work together in this ecosystem, in these supply chains, to put together a computer that's ultimately delivered to you. My Framework laptop, which by the way has done an awesome job locking down their firmware, licenses the BIOS from Inside. They use the open source EC firmware from Google. They have to work with Intel to make sure ME is configured in a certain way, to make sure that BootGuard can be configured in a certain way, which protects updates to your BIOS and other such things on your system that has to deal with keys. So there's software, there's hardware, there's firmware, there's keys, certificates, and all of that stuff that have to be coordinated. And guess what happens when something goes wrong? You get this. And this doesn't help anyone. I'm the end user. Microsoft says it's someone else's problem, but I updated Microsoft. Framework may say it's one person's problem. Dell says, well, that person should update it. Who's supposed to update this? This does not help us from a security perspective. And also OEMs make mistakes. If OEMs do a better job and they start producing more firmware, I'm all for it. That's awesome. However, they freaking make mistakes. MSI rolled out an update that essentially disabled secure boot, but from the user perspective, it was perfectly good. So secure boot was enabled, and it was checking stuff, and if something failed in a revocation list, it let it pass and said nothing. And that was a mistake on MSI. So OEMs make mistakes. We can achieve this like, oh, well, OEMs are getting better. Yeah, but OEMs still make mistakes. AMD just patched 31 vulnerabilities. Sometimes source code gets leaked. Sometimes keys get leaked. If keys get leaked, it undermines the entire security framework for your PC server or laptop. If someone loses a key, you're screwed. Fortunately, the boot code keys, Intel boot guard, I should say, that were leaked in that were development keys and they weren't put out to production. We dodged a bullet. If that had not been the case, that means attackers could basically own your system and the low-level firmware that's on it because they have the key to do that. All right, some potential solutions. It's perfect timing, actually. So Richard Hughes is completely awesome. I'm going to spend more time with Richard because he's doing great work at the LVFS, Linux Vendor Firmware Service. This allows you to update your firmware on Linux. He's doing an amazing job. OEMs can submit firmware updates. It's being put into the Linux ecosystem. You can update your secure boot keys. Ignore when you go read my article, which I know you will because I'm going to link you to at the end, on how to update your DBX on Linux. Ignore that and follow Richard's directions. If you have questions, contact me. I'll help you with it. It's pushed forward the DBX updates in Linux in a huge way. Richard also has helped with the host security of some of your firmware. So a little known thing, if you put on a modern Linux system, I can't remember which version, but FWUpd is the service from Richard that goes on your Linux system. FWUpd Manager Security -- Force will perform a security audit of much of the hardware and firmware on your system and tell you if things are wrong. You can see my screenshot on the left. My spy lock is disabled. That's not flash lockdown. The configuration has been locked down. That means there are some missing protections on my spy flash. So this is starting to get worked into more common software that's included with more modern Linux distributions, which I think is an amazing thing. So this talks about boot guard and a bunch of other things. It's a great thing to run on your Linux systems. If you haven't messed with it, check it out. And please contact me if you're messing with it and you don't understand the results or want to learn more. I will definitely help you out with it. I've been using it in all my systems to keep my firmware up to date, to perform these security checks, and to update my DBXs on all of my systems that I manage, which aren't just my personal systems. I have systems in production that actually still run the podcast, and I've used it to update all of those systems as well. It's gone amazingly well, and the project is doing great. I want to see more from this project and support. Update your firmware. Easier said than done, as we all know. Like we all have scars, gray hairs from updating firmware. I know, I get it, I do too. You see the gray in my beard? A lot of that's from updating firmware. You still need to do it. And people can still blow up your computer. This is recent research that like this weekend I was adding into the talk. This is research, a paper that was produced. I validated this with several experts in the field, and they absolutely say this is a real thing and it's possible by using the BMC, which frighteningly I showed still had default passwords enabled. The power management bus can be activated to permanently damage, and not just Intel Xeon. I have from good sources, it goes beyond Xeon PCs. This is something you need to pay attention to, because this is not even the spy flash stuff I was talking about. This is physically damaging your computer remotely. Everything I talked about today is remote access, without physical access, without clipping onto a chip or opening up your case. You can damage the spy flash, and in this case, from everything I can tell and experts, blow up a computer remotely. So, what's the future? I want to continue to raise awareness. I want to upload spy flash images to a central community project. I'm looking for people to help me with this. I'm looking to gain support. I want a dump from your spy flash. I want to be mindful of what data is on there, and I don't want to compromise anyone's privacy. But this is critical to understanding if Tyler wants to buy a laptop and I have that laptop, I can analyze my firmware, but Tyler has to know that I have that. I want this community. I want you to go to a website like VirusTotal and go, what's the firmware look like for this laptop that I want to buy one of for me, or I want to buy 15,000 of them for my job. Is it coming from the OEM securely? I think that will help, and I'm looking for help with that project. There have been some previous attempts with it. Also, I want to scan firmware updates for weird things. I want the MSI thing, the disable secure boot, I want us to know about that before anyone puts out that update. I want to have a virus total-like thing that goes, hey, MSI just put on an update, we friggin' scanned it, and we go, oh, it disables secure boot, you should not apply that update until they fix it. Those are two things that I think are big in actually solving the problem. This talk was made possible by people way smarter than I am. I am just the evangelist for a lot of this stuff, but Alex, Yuri, John, all of the people that I work with at Eclipsium, and all of the people that have done research previous to this that I have read and tried to understand, I am on the shoulders of giants. These people have done amazing research. There was a talk at Hardware I/O. I love this slide. Just a little bit about me. I do a podcast and I work for Eclipsium, and I'd love to talk with any of you about trying to solve some of these problems we have with firmware. And make sure I will publish these slides, I promise, and these are all the things that I worked on that kind of led up to this talk that dive into a lot more details in some of the areas. So, thank you. I can take one question, and then we can take more questions for as much as you want in the hallway. One question.
Yeah, so exactly how does this really affect TPM? I mean, obviously this seems to happen before TPM kicks in, so does that completely alleviate the concept of TPM?
Yeah, the question is, how does TPM either like help or support this process? Largely, this stuff is outside of TPM. When I talk about the boot process, how UEFI works, how firmware updates work, to my knowledge, and I'm not a TPM expert, this falls outside of the TPM process.
So it's...
I don't think it invalidates the process. I think TPM is used for something different, but again, I haven't started studying. We're working on a project to evaluate the TPM on your computer. So I can tell you a little more about that. But again, in my research, I haven't seen where TPM could help or hurt this process.
So I'll take that question.
Yes.
It depends on the chipset. If the TPM is part
The answer is always it depends.
if the TPM is not a discrete module, but it's part of like Intel ME or AMT, all this applies. If the TPM is a separate chipset, then maybe it could measure, but if you brick the boot, like the low levels of this, the TPM never gets power.
Right.
Like it doesn't start, right? It still has to load before it can measure to keep going.
So why use TPM if you can circumvent all of this?
Because, well, this could brick the system, sure, and you could prevent it from booting, but somebody could also, in some of the higher layer OEM sections of that, memories, words, could load something malicious. So the system comes up, but there's a malicious payload in there that might, I don't know, say rewrite your root password or siphon stuff off, and the TPM could measure that.
I'm asking a question wrong, we can talk after.
Cool.
Thank you.